Hello, everyone, and welcome to the TU Delft Library. My name is Vincent Salucci. I'm a program maker for the library. And this, let's say, these last 2 quarters, we're looking at the theme of female researchers in robotics and female-led robotics research teams. We have a really nice exhibition titled SHErobots, Ecologies of Care, which is over in the corner of the library here. So I hope you have had a chance to check that out. And if you haven't, please do, because it's the last week. I think next week is the end. We're dismantling. So we worked on with a trio of researchers from the University of Sydney and New South Wales, and they're very much involved in design and robotics. And the exhibition curates over 27 female researchers from 8 or 9 different countries working within the field. And then for the side program, we wanted to connect those with the female researchers in robotics at the TU Delft, which leads us to the SHErobots Cafes series, lecture series. And we have the goal of it. My main goal was just to bring get as many robots in the library as possible. So we've succeeded in having several robots, and I think we have a few today to show off related to medical robots, and soft medical robots, and soft maritime and transportation robots. And we have a team of researchers that are going to show, and I apologize, I'm going to let the two younger researchers introduce themselves when the time comes up, but I'm going to go ahead and begin by introducing the lead researchers. This is Aimée Sakes, is an assistant professor at the Biomedical Engineering Department, where she earned both her MSc and PhD titles with honors. Additionally, she is a board member of the Applied Sciences domain of Dutch Research Council, NWO-AES. In her research, she translates robust solutions from nature into smart mechanical systems for solving challenging problems in the medical world. And I've worked a little bit with Aimée in the past, and I'm also very inspired by her use of biomimicry in her devices. And then Jovana Jovanova is an assistant professor in mechanical engineering at TU Delft, and her research is focused on large-scale adaptive metastructures, mechanisms, and machines. She also develops model-based design frameworks for adaptive machines and large-scale soft robotics. So I will turn it over to our speakers, and we'll come a little bit back after the presentations, do a small discussion panel, and then we'll get to play with some of the demo robotics. So enjoy.
Thank you. How do I turn this on? Hello. All right. Hi. I do not always speak with microphones, so I'll get used to it. Welcome, everyone, and thank you for coming. So yes, I'm Jovana Jovanova. And today, together with Aimée and our students, we would like to show you what we are busy with in our daily life. Today, we'll try a bit something different, so we will take turns in telling the story. So it's not going to be one then the other, but we will just switch in between. So yes, I'm Jovana, then...
Hello, I'm Aimée. Thank you so much for the introduction as well.
I'm Vera. Hello.
And this is us a couple years ago in Singapore, where we presented our work at the RoboSoft conference. Yeah, aside from doing cool work that we will talk and show you about, we also find it very fun. I guess the question might be in the title, why do we want to talk about soft robotics in medical or maritime? So this is a standard challenge for robots to open a door. And we have sophisticated robots, but when it comes to a simple task like opening a door, you see what's happening. So what do we need instead? How we can actually have robots who are very sophisticated execute tasks that are adaptable, versatile, and compliant. So we need to add softness to the robots. So in the day of ChatGPT, we asked for a definition, what is a soft robot? And this definition maybe is changing day by day, but when we did the presentation, it says a soft robot is a type of robot that is made from soft, flexible materials, such as silicone or rubber, rather than from rigid metals and plastics. Soft robots are designed to be able to adapt to their environment and move in ways that are similar to living organisms, allowing them to navigate complex terrain and interact with their surroundings in a more natural and flexible way. Because of their flexibility and adaptability, soft robots have potential applications in the field of medical surgery, search and rescue operations, and space explorations. So I hope this gives you a nice idea of what soft robotics is about, and why we want to work with soft robotics is because when we look around us in nature, biological bodies have highly complex shapes and are soft and deformable. But conventional robots, we cannot describe them in this way. So if we can achieve particular and more complex behavior, like in nature, then maybe we can really use soft robotics for complicated tasks and computational tasks. So this field has been, I would say, developing in the last couple of decades, and we have seen different types of robots that really take inspiration from nature. So here you can see from different types of fish to octopuses on how they actually move and how we can mimic their movement for robotic tasks. We recently worked together with other scientists, and we published this paper that is on diversity and inclusion in soft robotics. And one of the things that actually thinking about this, what we explored is that the future of robots will be in all kinds of applications. So from agriculture and maritime and health and industry, and they will have to interact with with people and with the environment around. So in order for us to really develop robots who are future-proof, we really need to take this in consideration and design robots who can take their interactions with the environment and with their interacting people in consideration so that they can execute better tasks. Based on the application, you can see here we have from medical to maritime. That means that the scale changes. So if we talk about medical, then we have very small robots that go into our bodies, or if we talk about underwater or offshore robotics, we might have very large machines. In terms of diversity, these robots, we envision them to be operated also by a diverse group of people, which also needs to take into account these kind of differences. So talking about applications, you can see here we have really different tasks. And most of these tasks are very challenging for the conventional robots. So from inside the human body to disaster relief or underwater exploration, all the way to remote operations or handling meats or fruits and vegetables. Even parcel sorting, that is with different shapes and forms, needs to have adaptivity and softness into their designs. So at this stage, I give the mic to Aimée.
The surgeon dreams of helping more people. She also wants to do it in a better way. But with a growing and aging world population, it becomes even harder to help everyone. Although surgical tools and hands are already quite precise, they are too crude to safely reach the unknown and undefined environments deep inside the body. So how do we enhance the precision of medical procedures while also making sure it's replicable and affordable? Could technology help us further? We already use robots for precise tasks, but there is one problem. The robots that we have right now are too rigid, not flexible enough, which makes them unsafe for these kinds of procedures on fragile, living and moving organic tissue. For that approach to work, we bring together specialists from biology, engineering, design, sensing and control in a close and intense collaboration. Within the Soft Robotics project, we will follow a bio-inspired approach. We study the functional principles of shape, movement, control, and sensing of soft biological systems and reverse engineer them into mechanical and control concepts. We will design and build advanced soft robotics that can be soft and hard, move and deform flexibly, and sense their environment. We then test prototypes before making the new soft robots available for the market. Only when we're able to produce affordable and operational robotics that we can replicate, we scale up. And only when we scale up will we make a difference in the world, making possible what our surgeon previously thought impossible, performing better and more operations than ever before. And who knows where else our bio-inspired soft robots may come in handy.
So this was just a short video that was made about the work in the Soft Robotics Consortium, which is a 4TU project. And I'm mainly focusing on like the surgical side. So as you could see in the video, we really need these soft robots in the medical world to avoid damage to tissues. Because nowadays we have rigid robots and they can cause damage. If you even touch, for example, a blood vessel that's small, it can rupture and it can lead to severe bleeding, for example. And also, like if you look more towards exoskeletons or rehabilitation devices, you need something that's comfortable to wear, that's soft, that like adapts to the body. Also, like I often work in the cardiovascular field, so with the heart, and there you have to go through complex vasculature paths in order to reach, for example, deep inside the heart to perform surgery. So you need something that's very flexible, but also has a lot of joints. So. And also, of course, there's blood flow in there. So if you're inside the heart, there's very complex dynamic flow. And you still need to be able to control your device and be able to for example, go and perform your procedure. And of course, I'll bring the floor back to you.
Yeah, so why do we need soft robots in maritime environments? If you think about underwater robotics, and if we talk about exploration and interaction or inspection and maintenance and rescue missions, all they have in common is that there is interaction between the robot and the surrounding. And for that, we definitely need softness or flexibility in a way to execute these tasks. And then if we talk about maritime transportation, then what we need is we need machines that really can adapt to their environment, and the environment outdoors can be really dynamic. So this adaptiveness is the key.
So what did the medical field and the maritime environment then have in common? You'd say they're very different, but I think they're also quite alike. So if you look into, like the maritime environment is a fluidic environment. Well, I work in blood vessels, so it's also fluid. And also it's very dynamic, so we have flow, we have currents, we have all these things. And there's also often, like for example, in deep sea, there's difficult to reach areas, you need this flexibility. And it's also often unpredictable. You don't know exactly where you need to go, what kind of course you need to take, because it's a natural environment. And of course, there's also delicate structures. Think about corals in the maritime environment, but also, of course, blood vessels or other organs. So we think actually there's a lot in common. That's why we also work together. And we're working together actually to create intelligent soft robots for both the maritime and the medical world. And we'll talk a little bit more about that now. So of course, there's like, if you think about intelligence, there's many different types of intelligence. And of course, the questions arises, how do we incorporate intelligence into soft robots? And what is intelligence? So would you consider like a single cell organism intelligent, or are plants have a type of intelligence, for example? And these all, there's all these different types of layers for intelligence, which takes into account the body, but also the brain. And this Vera will tell a little bit more about.
Yeah, okay, so there are multiple perspectives on intelligence, depending on which research group you are going to. And a really big research field is, of course, artificial intelligence. So artificial intelligence is more focused on the brain of the robot. It tries to optimize the central processing, the control. But then there's also a new popular field, which is super interesting. It's called embodied intelligence. So in this field, the focus is more changing from the brain to the body of the robot. So the body is designed in a way to make the control of the robot easier. So in that way, part of the intelligence of the robot is embedded inside of the body of the robot. So that's super interesting. And a really cool example of an animal that embeds embodied intelligence is, of course, the octopus. So if you take the octopus arm as an example, it can make 3 really typical smart motions. It's reaching motion, it's gripping motion, and it's fetching motion. And yeah, you can see in front of you, the octopus arm is, of course, totally soft. It's super flexible, so it can move in all directions. It actually has kind of infinite amount of degrees of freedom. So this would be very difficult to control. But the octopus incorporated some things in the design of its arm, which makes this control easier. So we can first look to the reaching motion. Here you can see an octopus that tries to catch a fish. So what it does, it creates a bend in its arm. You can see that here at the yellow arrow. And then it points this bend towards the fish. And then it just pushes the bend forward towards the fish. So that means that the amount of degrees of freedom is limited a lot, because it only has to decide for the angle and then the position of the bend. So that's very interesting. Here you can see again this rolling motion. And here at the left you can see the smart orientation of the muscles inside an octopus arm. So this orientation of the muscles and its material properties makes that if all the muscles squeeze together in one segment, that one segment stiffens. So it uses this mechanism to push the bend forwards. So it stiffens one by one the segment in its arm before the bend, and by that it's pushed forwards. So that's a very smart behavior in the design of its arm. And what is also very interesting is that the shape of the arm is optimized for this rolling motion. So the diameter of the arm becomes smaller and smaller towards the tip, and it also becomes flatter. So that means that the drag forces are smaller. Yeah, and it's more energy efficient and more stable to make this rolling motion. So that's a bit where our research is also focusing on, to make such a smart, soft, rolling arm with different sections that show different behavior depending on the environment. For example, contraction, elongation, bending, but also this variable shape over the length in a smart way. Then you have the suction gripper of the octopus. So the suction cup of an octopus works super good. Way better than our suction cup that we are using in the kitchen, because an octopus can catch fish or attach to very rough rocks. Our suction cups can't do this. So the suction cup is designed in a smart way because it's divided into 2 parts, and both parts are optimized for their own function. So if we look to the top part, here's the suction chamber, and the function of this part is to generate suction. So the muscles around the suction chamber are optimized to make this very stable and strong suction force. And then the bottom part is in contact with the target surface. So the function of this part is to create a seal. So the suction cup is not leaking. So this part is optimized to perfectly adapt to the shape of the target surface to create this strong seal. So by separating these 2 functionalities in 2 parts, the suction cup is able to be optimized for the both functionalities. So we took this as inspiration to develop a octopus-inspired suction gripper to be used in minimally invasive surgery, for example, to grasp very slippery and flexible tissues, which is very difficult to do. So just like the octopus, we built this suction cup with different layers, and every layer, this is the suction cup, is focusing on one functionality. So there's a layer focusing on foldability, one on air tightness, one on slidability, and one on the creation of this seal. here in the top, you can see that this suction disc was able to attach to a wide variety of objects with different curvatures and flexibilities. And in this video, you can see how it's able to grab a chicken heart, if it's able to play. Yeah, so this chicken heart is super slippery and very small, and still this suction cup is able to create a seal. And then we were also interested in embedding a sensing method in this soft suction cup. So we collaborated with AMOF, which is a research institute in Amsterdam. They developed a very interesting sensing method. They measure the vacuum profile in the suction tip over time. And by doing this, it can sense what kind of tissue it is gripping. If it is very flexible tissue, because then the tissue is more pulled inside the suction disc, so then the vacuum profile is different. And with a very rigid tissue, for example, cancellous tissue, this tissue is pulled less inside the suction disc, so the vacuum profile is clearly different. And the next step will be to detect slip with this sensing method. So the point when the suction disc starts slipping, the attachment is becoming broken, you would really want to know when this is happening, because then you can add more vacuum pressure. And you can also sense this by the difference in the vacuum profile of the suction cup. This is, again, a video of this sensing method. Okay, and then we were thinking, we want to make this suction disc, but not pneumatically actuated, but magnetically actuated. So we embedded magnetic particles in the flexible membrane of the suction disc to create this magnetic intelligence in the membrane. And because of this, the membrane is attracted by a magnet. So a suction chamber is created beneath the membrane, and it can work as a suction gripper.
And there it shows that it's stick.
It's very. That is the magnetic suction gripper. Here you can see also some videos. At the left is a video in which the gripper is picking up an apple, and oh no, at the right, and at the left it's picking up a grape. Yeah. And then the third motion of the octopus is also very interesting. It's the fetching movement. So the octopus has caught a fish, and then it wants to move it back to its mouth. So the octopus can actually catch this fish everywhere on its arm. And then it creates 3 elbows. You can see them here at the arrows. These arrows can be created anywhere on its arm, depending on where it's catching the fish. And then it just moves it to its mouth. So actually, it transforms into an arm just like our human arm with 3 wrists, 3 elbows. So this also makes the amount of degrees of freedom lower than when it would be able to move in any kind of direction. Yeah. So
I'll tell a bit about another type of intelligence that exists, and it's called morphological intelligence. And it's very similar to embodied intelligence, but a slight difference is that it's a little bit more focused on the body itself. So for example, things like the chameleon tongue, does anybody you know how that works? Any guesses? I always thought myself there was like a type of roll-up thing, so that it just unrolls. But actually what it uses is it has a type of tongue skeleton, a bone. And around that bone there's a elastic layer. And around that elastic layer is a muscle. And when it contracts its muscle, it elongates the elastic layer. And then once it reaches the end of the bone, it sort of releases that energy and it shoots off the bone. So it's quite interesting system. And also, for example, the elephant trunk is very interesting because it's also similar to the octopus. It uses a lot of like bending waves to create motions, for example, but it's also very stiff. And for example, it's been shown that the skin of an elephant trunk is also very important to create this. So it's very interesting, the pleating. So, for example, what we've looked at in our lab is that we look into the wasps, mainly the parasitic wasps, and they're also very intelligent because they have a really, really long and thin stinger. And with this stinger, they're able to penetrate wood and place their egg, for example, inside a larva in the wood, or also they sometimes do it in fruit. But it's interesting because it's so thin that normally it would buckle, but it doesn't. So how does he do that? So actually, if you look closer, the ovipositor is made out of 3 parts, usually 3 valves that can move independently, as you can see here. And what it does is it pushes down the purple valve, and then the blue valve, and then the green valve, and it keeps repeating this. So what it does, it's only pushing a small amount and makes like this kind of reciprocating motion. So you can see also an actual wasp. And it's also able to steer. It's very interesting. It can, for example, push one valve a bit more forward and create a pre-bend, and therefore it can, for example, also steer, as you can see in the video here of a wasp actually trying to reach a certain target in a gelatin phantom. So actually this stinger is very interesting because first of all it's long and thin and it can propel itself through wood or other substrate, and it can steer. So what we did was we, based on this principle, developed different types of needles, which you can see here, made out of nitinol rods that can also use this reciprocating motion. And we are also able to steer these needles by making a type of a bevel tip, similar to the wasp. So what happens if we have a bevel tip at the front, we get a resultant force that's like a 90-degree angle with the tip, and then you can deflect the tip to the right, or if you put the bevel tip on the other side, you can deflect the tip to the left. So you can steer it that way. Of course, these steering angles are quite large, so you can't really go 90 degrees with a really small radius, but you can still steer. So here you have a little video of the needle. Let me just skip forward a little bit. What you can see is that the needle, we form like first a bevel. So we change the order of the needle segments. You can see them here moving forward slowly to create like a type of bevel shape. And then once we create the bevel, then we can self-propel and then we can steer at the same time. So here it should start moving soon. So now it will start moving forward. And there you can see it go. And although it's slow, you can definitely see that it's slowly moving upwards. So we can see that we can steer here. So that's very nice. So if, for example, you're in the human body and you want to take a biopsy to see if it's cancer, then you can steer this needle towards that field. So we also looked into the other way around, so having like a type of hollow needle that can take things out of the body as well. And there we came to this device, which is a similar principle. It uses this reciprocating motion, but then it is hollow. And here you can see a video of it. So this is the whole device. with a motor in the back. This is a gelatin tissue phantom here. And you can see that there's a little tissue here. And then we turn it on here. And you can see the tissue slowly disappearing in the lumen. So it's being transported out. We also have the device with us, so I can show you, I'll give you a demonstration of it later as well in real time. But here you can see it going through the lumen, and then in the end it comes out at the handle side, so you can take biopsies or decide if it's tumorous tissue or benign. We also made a flexible version out of it so that we can actually steer and come to more places as well. So then we're a little bit about physical intelligence, which is another type of intelligence again. So there's so many types. I thought there was one type before I started this journey, but apparently there are more than one. And this is more about like the body itself, making things a bit easier for the overall and adding extra functionalities to the body. So for example, gecko feet have these hairs to stick to surfaces, which allows them to climb vertically and even on ceilings. So there's also research that's now being executed by one of our master students. He does a lot looking into shark skin. And shark is actually a very interesting skin that has a type of scales called denticles. And these denticles actually reduce drag, and they also have been shown to increase lift and also reduce the cost of swimming. It's more energy efficient. So we found it both very interesting because for me in the medical world it's interesting because we want not less drag in the blood vessels, and also of course in ships and other maritime applications it's very interesting to have this property. So we looked into what research was done, and we found that if you look at the body of the shark, there's different types of denticles based on where you look. So at the nose of the sharks, they are shaped differently from the sides or at the tail. And a lot of the research was done actually on dead sharks. So there's not much research on live sharks. So now we're currently working with Blijdorp to also do measurements on live sharks and how these denticles work and how they decrease drag on actually live animals that still move, that are not preserved. And we're also looking into the bristling effect, and that's more about that some sharks can change the angle of their tentacles, and thereby they can reduce drag or influence the drag of their body. So our student made this design of the tentacles that we can control the angle. And here you can see one of his small tentacle that we made that can change the angle. So during swimming you can, for example, change drag. So you can go from very low drag, and if you want to stop suddenly, you can increase the drag drastically to quickly stop moving. And next step is we're gonna miniaturize this. So then I give the floor back to you.
Yes, thank you. So I would continue talking about mechanical intelligence, and this is something that what we have come to realize is that when we want to design for a certain application, if we know the environment and the changes in the environment, then we can take that into consideration in the design itself, and then have the robot adapt to it or even self-power from it. And the way that we explore this, so we do bio-inspired design together with Aimée. We look into variable stiffness, we look into metamaterials as a concept, but we also look into stimuli responsive or smart materials. And here is a video that summarizes the research of my group.
As the world becomes increasingly connected, the machines need to adapt to their working environment. Adaptive machines can revolutionize many industries, including maritime and transportation. This is why TU Delft is designing the next generation of adaptive metastructures, mechanisms and machines, led by Assistant Professor Jovana Jovanova at the Faculty of Mechanical Engineering. Adaptiveness can be achieved by understanding the varying operational conditions, translating them into functional design requirements, and systematically develop innovative solutions. Jovana and her team are designing adaptive metastructures, mechanisms and machines able to change their properties and functionality to improve their performance. For example, the offshore industry is continuously exposed to extreme conditions. To better understand the dynamic interactions between the harsh environment and the vessels with their equipment, JamLab works on developing fast and reliable models. Then they're used for model-based design and optimization of specific applications like underwater vibration attenuation. With the open sea providing new opportunities for energy transition, adaptive structures can play a key role in unlocking this potential. Furthermore, JamLab integrates the concepts of compliant mechanisms, smart materials, metamaterials and soft robotics into the design of mechanically intelligent structures responsive to varying operational conditions inside industrial facilities or outside in their natural environment. The inspiration for mechanically intelligent structures often comes from observing morphological intelligence in nature, whether it is the dynamic stiffening of an octopus's arm or the ability of an elephant's trunk to lift 300 kilograms. In the JamLab, models are developed to capture the behavior of different smart materials like superelasticity or shape memory effect, stimuli responsiveness in hydrogels, or piezoelectric effect. They are crucial to efficiently design unique functional unit cells into a complex, patterned shape morphing architecture. The combined effort of nonlinear geometry and smart material behavior is captured into the building block design method. JamLab supports activities within TU Delft, nationally and globally, to promote science and wider social impact. Adaptivity is key. Join us. Contact us at j.jovanova@tudelft.nl.
So I hope this gives a bit of flavor of what are the applications that we look into. As you said, at the core are these mechanically intelligent structures that are programmed by design to recognize the changes in the environment and respond in the desired way. And how we usually do that is we try to combine material and patterning or certain geometry in the design phase. We typically start with a structure or a certain generic design of a structure, and then we have geometry and material. Then we try to apply stimuli that comes from the outside. That can be temperature change, magnetic change, electric, magnetic field. So anything that can change in the environment can be a trigger. We can also induce this change if we want to for control purposes. And that results in a shape change. So that is how we actually embed intelligence or smartness into the structures themselves. And one way to do that is through smart particles. And Aaron is my PhD student who will tell a bit about his project.
Okay, thank you for Jovana. And I will talk something about the magnetical intelligent structures based on the smart materials and through the model-based design method. Okay, so Jovana and Aimée, they talked a lot about why we use the soft robotics used in different applications and what are the benefits of the soft robotics or soft structures. But I want to say that as for the soft robotics, the key part is the actuators. So different from the rigid robot, a lot of joints and with rigid parts, soft robotics always supported by the soft materials, which means the linear properties of these materials make it more difficult to form or organize a complex structure. So the actuator is the key. There are a lot of ways to form the actuators, including a lot of conventional method, and you have already looked before, some pneumatic or fluid method. And the smart materials recently becomes a hot topic that can be used into soft robotics that achieve the intelligent structures by some smart ways. Because our background is the maritime and logistics, the smart material, the soft robotics always now used in the small scales from millimeter to centimeters. But if we want to make them into more widely applications or more large scales, still some problems we need to figure out. So in our project, we would like to use the model-based design to try to develop some structures with the intelligent magnetical mechanism, or use smart materials as the base to develop a new generation of actuators. In the first design, we're trying to use the particle as the medium to actuate the soft structures. As you can see here, we use a different size of particles as the actuating method to actuate the soft structures to have fixed behaviors like bending. And we do the model-based design and compared with the experiment's results. And they have a very good agreement. So that means our design works. And the second part, we use the smart material as the medium to develop a new generation of actuator. And first, we are trying to use smart hydrogel. Maybe some of you heard about hydrogel. It's a kind of smart material that can have the swelling and shrinking behaviors by different stimuli. And we try to develop a kind of model to describe the linear properties of hydrogel, and this is the result. And based on the hydrogel properties, we're trying to develop the first designs combined with the hydrogels and the conventional hyperelastic materials like silicon, and make two layers structures. Maybe you can have some video, please. So to combine the hydrogels and the silicons, they can achieve different behaviors like bending and some more complicated curve forming, and to form a real gripper. And okay. And then to combine with the hydrogel with the hyperelastic silicon, we're trying to develop a new, the next step, the actuator with the hydrogel balls inside and some silicon cover outside. You can also see some demos in the table later. And after activating all of the hydrogels, we can get very ideal behaviors of bending and can reach a different bending angle that can apply it in the real applications of grasping or in some applications of offshore engineering. And this is some configurations by the different designs of the combination with the hydrogels and the structure design. Of course, all of the structures are designed of silicons with the hyperelastic properties. Okay, and then as we know, the softer materials, they are very soft. They are, of course, have high adaptabilities and flexibilities. But the one challenge is that the softer materials always with low loading capacities because of its material property itself. So we are trying to embed it with another method to enhance the stiffness itself. So the bending stiffness is also another key point that in reality applications, like if you when you want to grab something, of course all of the objects have its own weight. So you have to at least reach the minimum loading requirement to grab something successful. So we embedded some different low melting point alloy to increase the stiffness. And here are some results. Compared to other designs, our proposed actuator can both increase the adaptabilities and achieve the high stiffness. Based on this, we are trying to develop a new actuator by combining the hydrogels with some other smart materials. Because in the end, our goal is to develop a 4 automatic system that without any extra source to drive them. So it can only activated by the environment change or by the environment stimuli. In this step, we are trying to use the hydrogel combined with the shape memory alloy to both achieve the large deformation behavior and the stiffness change. Maybe some of you heard about shape memory polymers. That's also a kind of smart material that can change its phase. So from the rubbery to glassy phase through a transition temperature point. The key parameter of the shape memory polymers that its elastic modulus can change a lot by jump over the transition temperature. So use this property, we can also develop the structures with stiffness variation. This is the actuator I designed before. So the cylinder cover can inside with the active or inactive hydrogels. And after you lowering down, increasing the temperature, so the shape memory polymers now stay in a rubbery state. So it's very soft and can be deformable. So after you activate the hydrogel, the whole actuator can swirl, or like the volume can change a little bit. And after that, after you lowering down the temperature below the transition temperature, the whole of the actuator can be in a stiffness state. So all of the shape will be locked. Based on this, we are trying to develop the smart actuator-based design, like the meta materials, to achieve bending behaviors and also the curling behaviors with more complicated shape morphing structures and the elongation structures. So the difference is instead of 2D designs, now we use 3D designs to figure out how the smart actuators behaved in more different ways. That's it.
Thank you, Aaron.
Thank you.
And in general, I just want to wrap up with a couple of examples why it's interesting to look into soft robots for marine applications and get inspired by marine animals, is because a lot of the marine animals, as we said, octopus or others, have a lot of flexibility, and then they can really exhibit complex tasks. So if we can mimic their behavior or get inspired by their behavior, then we can design grippers for manipulation, because that is something that when we need to inspect something or we need to manipulate something, or for aquaculture, if we want to harvest something, then we need to be very gentle with the touch and the interaction that is happening in the environment. So this was a project that we worked on where we used shape memory alloys. So we trained wires for actuation, and then we developed a grip around them in different configuration to be able to really manipulate different tasks. So you can see here we have from stone to something very squishy, and we were still able to capture it. Another maybe interesting application to think about with we work together with a company for cone penetration testing. So that is a typical procedure done if we need to extract soil properties. So now in offshore especially, you probably have been recently somewhere in the coast in the North Sea, and you see that there are more and more windmills popping up. Which means that every single location of the windmill needs to have cone penetration testing done to extract the properties at the location. And how that is done right now is really, it's a massive logistics challenge. So you have a vessel going, and then you put a structure, and then you have big hydraulic actuators that push a rod into the soil that at the really tip has sensing data that can extract the properties. And then together with the team here, we're thinking that, well, the animals, for example, worms, are doing that in such an easier way. So maybe we can take the inspiration from earthworms and design self-propelling, self-burrowing probe that can do the same job. So go to a location, burrows itself into the soil and extract properties. And this was just a student who looked into it. And what he did was he really broke down the movement of the earthworm in different motions. So what is elongation, what is radial extraction, so that we are able to mimic those motions and then be able to penetrate. And here in this design, he also used shape memory alloys for actuation in the radial plane. I mentioned the windmills, so we are going to have more and more windmills in the North Sea, but also everywhere else in the world, so that it can support us in the energy transition that we are all fighting with, and we're trying to keep up with the challenges that are facing us, also the policies that are in place. And to make this even more feasible, what we need is to have really robotic inspection and maintenance in everything that is happening offshore, because offshore is becoming more and more populated. So windmills is one thing, but also aquaculture. So more and more processes are happening in the water. So we do need robots in the air, so drones, surface vessels, so ships, but also underwater, to actually perform inspection and maintenance tasks to be able to really be economically feasible. So in terms of the maritime side, I do think that really we do need soft robots that have embedded intelligence to really unlock the blue potential coming from the water and the ocean. If you have seen this, this is Theo Jansen's Strandbeest, so they're beautiful artistic entities that when they're on the beach, they're really cool, and I think that also us as engineers can get inspired to really use the environment as a driving force and design the next generation of robots. So yeah, we would like to thank you all. So this is a picture of my team. Some of them are sitting in the audience. Thank you all for coming. And then we would like to invite you for a challenge. So one of the challenges that we would like to play here is you are all invited to come to pick up different things with really a simple soft gripper design. Yeah, so with that, thank you very much.
Maybe we can have just a few questions. I can maybe get us started, and then we'll have a few questions from the audience, and then we'll make sure to go get the gripper challenge in act. So I was very pleased to see that you had the paper that touched upon the D&I issues in this massive scope and very cool scope of the soft robotics that you're approaching. And I was just curious if maybe you could give us a couple examples from some of your research of, let's say more, I mean, we know kind of the crash test dummy sort of thing, but maybe more medical and transport-related maritime.
Do you want to start?
That you've come across, even more personal maybe.
Yeah, so this paper was also to show that in like soft robotics, there's a lot more diversity. If you look at like men and women, but also like younger researcher and older researcher, and you see that this diversity is really necessary to also drive change. So you really need like a diverse set of people, diverse set of backgrounds, because of the large application areas. So I think if you, for example, look at academia as well, you can see that there's still quite, for women, still quite a leaky pipeline. So you still have quite a lot of women in academia when they're PhD, but if you look at TU Delft and other, it slowly declines. And reasons that we found were like, for example, that it's often very difficult to combine a career in academia with like personal life for women, and so that's were a few things that we found in our questionnaire. But I think Jovana can.
Yeah, I
add.
would also like to add, I mean, one of the things that what we were looking into, let's say the future workforce, is that if we want to work with robots, that means that we need to have all, of course, all genders, but then also age, and then also, yeah, physical disability maybe, or different kinds of differences that we come across in our real life, which means that also robots need to be able to take that in consideration in their working life, but then also the differences need to be adapted into this co-working space. So we thought that is very important to bring to the table, that diversity is very crucial for the idea generation and for implementation and for the applications, but then also working with these robots, we have a diverse diverse set of skill sets in terms of the operators and in terms of the people that are using these robots.
Nice, nice. And I have one more question, and then I'll turn it over to the audience. And this is a pretty out-of-the-box one, so be prepared. But I'm just curious, because I think your field is so cool, and the fact that, like I mentioned before, the biomimicry I think is very compelling. I speak for myself, but I imagine the audience is very compelled by that as well. But I'm just curious too, is that, like, in some ways, has there been any conversation or researchers that you know of that are actually talking about, we had a previous SHErobots in which they were talking about assistive robots and stuff, so we're sort of taking the best of these species and then sort of taking, inserting and augmenting our apparatuses and devices with this. And I'm ever worried if there's any conversation about actually augmenting other species with robotics. I just told you it was out of the box.
Well, I guess the safest answer I can get to that is that at TUDAV that would not be possible, because legally we are not allowed to have animals.
No.
Yeah.
So don't worry about that, not here.
But I've heard some stories about like animals, not so much I think augmentations, but there are some like rehabilitation devices for animals, such as horses or something like that, so that they actually can like sort of train their muscles. But it's often very difficult with animals because they don't understand that they're being helped, so often these things break. But what we do it's a bit different, but we are like working together with Blijdorp, so we are actually also like investigating the animals ourselves. So not so much like looking into what's already known, but looking into like, can this animal do this? What would be possible? How would it react? So we're working, for example, with Blijdorp, looking into getting octopuses there, so we can explore their behavior. And also we're working with the sharks there to see how they use their skin basically to help with the drag.
Super cool. May I open it up to the audience? Neetja?
Thank you so much. It was very inspiring. But because I'm a big fan of the series and I come for every presentation, I just want to make a bridge between a previous presentation I saw on drones. It was really interesting because there was this drone that they developed for going to the jungle near Singapore and then analyzing and collecting data. And they had this very simple device for catching on branches because they wanted the drone to land there. So I was wondering, could also some of these devices that you're creating can be equipped, they equip the drones or other robots for more complicated kind of actions?
Yeah, I think definitely, because I think like now of course I know what you talked about, Shalua's work. So she mainly focuses on branches, but for example, if you want to land on like more soft surfaces, such as like leaves or something like that, maybe you need a different types of grippers, softer grippers, or if you have different types of surfaces you want to land on, I think this kind of work, such as using of suction or like soft grippers, can be very interesting, especially if you don't want to maybe damage the surroundings. I don't see many drones in in the water, but there are a few that can go from air to water. Maybe then you also want to be able to anchor, for example, there.
But are you also interested in looking in ways to collaborate with other researchers in the university for these kind of projects, or are you not there yet?
Yeah, definitely. Like I know her a lot, and she works on very interesting things. So we're definitely always open for collaboration, also in wider topics.
Yes, of course. I mean, same goes for me. I also know her. With her and with other, we have talked about different applications and really pushing the technology forward, that we can interact with the environment, with the objects of interest, with people. For all of that, I would say our work is feasible regardless of the applications.
Thank you.
Any other questions? Well, I think we want to get to the demos then.
Yes.
So
Please come forward and have a look.
Thank you very much.
Let's please let's extend a hand to our presenters, Aimée and Jovana and Vera. And our son. And I just wanted to conclude the SHErobots Cafe series to say that the end of the programming year gets a little bit more social and fun, and we're going to be looking at some film in our theme of SHErobots. So actually I have a really prestigious emeritus professor who actually taught me a lot about film, who happened to be in the Netherlands, and so she's going to do a film workshop on comparing the original Blade Runner and the 2049 Blade Runner at the Robo House, and that's put on in collaboration with the Asimov Study Association. So I think there's a few spots left of that if anyone's interested. That's next Monday. And then, of course, the big social evening, end of the academic year climax, in which we do or programming year, excuse me, we do an outdoor cinema, and we'll be showing the Blade Runner 2049. So I invite you all to join us on the green roof of the library for that next Thursday, weather permitting. So no rain, please. No more rain. And with that, thank you for joining us, and please come up front and let's check out the demos.